Well, hello everyone. I've just been introduced, but my name is Fletcher, or Dr. Fletcher Warren Myers from the University of Melbourne. Please bear with me. For me, it's actually 3 a.m. in the morning at the moment, so if I blank out every now and then, it's because I'm trying to go to sleep. I've been invited here to talk to you about a marking program, and this marking techniques, and these techniques were actually developed during my PhD and developed in Norway for the Norwegian salmon industry. I understand there is a plan here and part of the in Iceland to actually try and mark all the Icelandic farm fish and to sort of help with their monitoring program. I won't go into the reasons of into marking. I'm just here today. I'll just present how my techniques work, how we sort of detect the marks, and how it actually can be applied to Iceland. Right, so just to start off with, I'll give you a little bit of outline. So I'm going to talk about otolith fingerprint marking, which is a technique I've developed. Again, I said I'll talk to you about detecting marks. This is using a LAICPMS, which is a laser-based inductively coupled plasma mass spectrometry, which we do in Australia at Melbourne Uni. Then I'll talk about the 3 marking techniques we use. So we can mark fish via vaccination, via egg immersion and maternal transfer. I'll give you some details on that shortly. Also then I'll go on to a little bit about fish health. You know, do these marking techniques actually have any effect on the fish? And finally I'll talk about marking in Iceland. We've actually started a pilot here already just to see whether this technique can be used for Icelandic farm fish. So otolith fingerprint marking. What is otolith fingerprint marking? Well, first of all, what are otoliths? I presume most of you will know what an otolith is. It's the air bone of a fish. And our otoliths grow continuously from very early on in the life history stage, from yolk sac larval stage, right until the fish dies. And the beautiful thing about otoliths is as they grow, they incorporate the chemical signature of the environment around them. So whatever's in the water at the time, they'll uptake that and retain that elemental signature or environmental signature in the otolith. Now, as they grow, they continually grow every day, so every day effectively you get a signature from that day. But more importantly, once that signature is incorporated, or those elements are incorporated into the otolith, it's metabolically inert, so it doesn't change. It's there permanently. And it's because of these impurities that are incorporated, also the environmental signature, and as an example, some of the impurities are elements like barium, strontium, magnesium. We can actually manipulate these incorporation of these impurities to actually create our unique fingerprint signatures. Now I'll actually go in to actually explain how we do that, but I'm just going to use one element, barium. Now, not all barium in nature is the same. So barium comes in multiple forms. These are normally called the isotopes of an element, and for barium, there's four rarer forms of barium that we're interested in. The most common form of barium in nature is 138. So as an example, in your cup of tea, there was barium in there, and you can say 70% of that barium in your cup of tea is actually going to be barium 138, but there's also a bit of barium 137, 136, 135, 134. So, and it's everywhere. It's in your cup of tea, it's in your fingernail, it's in the little bone in your finger. So it just naturally occurs in nature. Now, what's interesting about this element is the ratios of these rarer bariums to the common form of barium are very stable. So anywhere in nature, you find the ratio of 137 barium to 138 is just under 0.16. That's about 0.157. And that's also the same in your cup of tea, same in your fingernails, same in the bones. And it's because of this consistent ratio that we find in nature that we can actually use this to create unique fingerprints. So just to give a bit more context back to salmon about that, we did a survey we used archival data of otoliths all across Norway, and we actually measured this barium ratio 1:7 to 1:8 in fish from 22 different rivers, and we actually found that the variation in that ratio is only plus or minus 1%. So in all rivers across Norway, there's very little variation, which is good. So we know that out in the wild, if we go and measure that ratio, this is what it's going to be. The second question is, well, what about time? You know, we know over space it's the same, but what about in time? Also from this archival data, we went back through 20 years of otoliths, and we see that the ratio over time is also maintained, plus or minus 1% in variation. So that's good. So we know out in nature, if we catch a fish in the wild, its ratios, that ratio of 1:7 to 1:8 is going to be always the same. So then we move on to creating fingerprints. So say this is our 4 ratios of the rarer bariums to the common one in the wild salmon. You can see I'd like to call it a fingerprint. The 4 little bars there, 4 little fingers. If we measure in a wild salmon, that's what it's going to look like. If we go and measure in one of our farm salmon, it's going to look exactly the same, plus or minus that 1%. But it's going to be the same. So then, because of this, what we can do, we can simply, if we can manipulate the amount of one of these rarer bariums in the environment that the fish is in for a short period of time, we can actually change that ratio for a short period of time. And then we can actually detect that ratio in the otolith of that fish. Because remember, as the fish grows, that otolith grows every day and it takes in that environmental signature. When I say introduce a rarer form barium, it's only got to be in the water, or it can be in a vaccine that goes into the fish, or it can even be in the feed that they feed to the fish. There's multiple ways of that fish to absorb an enriched form of one of these bariums. So to give it more context to that, so say this fish is in a bucket of water and we add a bit of barium 136, and it's only going to be in there for 24 hours, we can actually change that ratio of 136 to 138 while that fish is living in that water or being grown in that water. Again, that gives us one fingerprint or one code or one marker. We can actually then continue on and we can say to the bucket of water we go and add a little bit of barium 135. We can manipulate that ratio so we get a second fingerprint. We could do that to 134 and get a third fingerprint. So in other words, now you can see I'm actually developing effectively a new code in the otolith for that farm fish. And then we can go and detect that if we go and analyse that farm fish otolith, we can tell that that farm fish is actually, or its fingerprint signature is different from a wild fish. So the next question is, well, okay, so we can create codes. So how many codes can we actually make, or how many unique fingerprints? It simply comes down to how many different forms of rare barium we can manipulate. And basically it comes down to simple maths. 2 times the number of isotopes of that element, or 2 times the number of different barium forms of barium you can use, minus 1. So basically we've validated it. We've managed to use 4 different types of barium so far, so we know we can make 15 unique fingerprints. Put that into context for Norway, that's actually not enough, because in Norway they've got 1,000 different fish farms. They've got over 90 companies. So for them it's not enough to actually still distinguish between farms or companies. But here in Iceland it's quite nice. We're still small. From what I understand, these are the 5 or 6 companies. So basically what this means, if we use this sort of marking technique, we can actually make enough unique fingerprints so each company here would have its own fingerprint code, or basically its own barcode. So if that company's fish got out, or that company just wanted to monitor the amount of fish that are escaping, you've only got to analyse those fish, and you know those fish or escaped fish came from that company. Also, I'll just elaborate a little bit on that. If that company also knows its fish are getting out and they don't report it, and they know that the fish will be detected with a 100% guarantee, they're going to actually have a lot more drive to actually make sure that their fish don't get out. Or at least they will actually report that their fish are escaping, so we have a better idea of exactly how many fish are getting out all the time. So it will drive compliance, potentially. Right, so how do we actually analyse the otoliths? Well, we do this back at University of Melbourne in our geology lab. Again, I'll try and pronounce that word again. We use LAICPMS, basically breaking down, we use laser ablation, that's the LA part, and that's the second picture on the left. So the first picture on the left is a whole lot of otoliths glued on a slide, and then that slide gets mounted in this box, which is a laser, and the third picture here is the whole laser. And so we ablate the otolith material, then it's transported on argon gas through to the mass spec, and then that mass spec reads the amount of how much barium-137 there is, 136, 135. We also measure the amount of calcium and a few other elements just as reference points. Once we've actually got that raw data out, then we post-process it, then we calculate our ratios, and then we can tell what the different ratios are in that otolith. Just to give you an idea, this is a par otolith. The actual type of laser we're using is spot ablation. So basically what happens is you can see a little a burn hole. It looks like a hole's been drilled in the middle of the otolith where I've got that 157 microns. That's where the laser started on the surface, and it just goes tack, 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 tack. Sounds exactly like that. And just drills all the way through to the core. And so it measures the elemental signature in that otolith from the surface all the way through the core. So effectively it just does a measure of its life history. Put things in relative terms. So 157 microns might look quite tiny to you there, but in terms of laser ablation, that's a huge, huge hole. What we've done is we've standardised that hole so that regardless of what size otolith we use, we always use the same spot size so that we get consistent results. You'll see in a minute we use that same spot size on a very small otolith, and it pretty much takes up most of the otolith. So what does a successful mark look like? Well, this is a fish that was vaccinated in 2014 in a pilot trial. It's been marked with 137. So just on the y-axis here, so you've got the ratio of barium-137 to barium-138. And along the x-axis here, you've got 0 at the bottom, which is 0 sort of relates to A in that top corner picture. So that's the surface of the otolith. Remember, we're drilling down through the otolith in the direction of B. So 0 means you're coming across to 0 to 100 to 200. So you're reading from the edge of the otolith to the core. Now, this dark blue line here is actually where the fish was introduced to that enriched barium-137, and you can see we've massively changed the ratio of 137 in that time frame of the fish. But as we drill through to the claw, and I'll just say one more thing, the light blue line down the bottom here is actually a control fish. So we're drilling from the edge of the otolith with control fish all the way to the core. You can see that ratio is nice and steady, the same all the way through. So this is effectively overkill. We've used too much barium to mark this fish, but again, it was a pilot to make sure it works. The other thing we have there is we need to have a level of, true or false. Apart from this one looks obvious that it's marked, but we actually set a detection limit to sort of give us a measure of certainty that we know we've marked the fish or not. And how we've come up with that is we take the mean ratio in a control fish, and then we go 3.3 standard deviations above that, and then we draw our line, which is our red line. And we know if we manage to change the ratio of that line, we can pretty much guarantee that, with 99.9% sure, we definitely know that fish is marked. In this case, it's very obvious, but as we reduce the concentration of our marks, so we only have to use the minimum amount required to mark fish, this limit of detection is important. So just to guarantee we've got certainty, we know we've marked fish. Right, so that's basically how it works, or the background behind it. So now I'm just going to go on to the 3 techniques that I've developed during the PhD. So the first technique is marking during vaccination. I'll just sort of state these techniques, we try to develop them so that they actually integrate with the standard production of fish. So it wasn't going to be something new that fish farmers or hatcheries had to do extra to their normal production. We try and make, the techniques we developed, we tried to make them so that it's just normal run-of-the-mill everyday production, and farmers won't even realise they're marking fish or having to do extra work. So we're trying to minimise the amount of extra work while still ensuring that all the fish are marked. So for this technique, marking during vaccination, there is 2 publications on it if you want to go away and read about it further. I'm just going to give you a brief sort of overview of how it works. Like I said, go read the publications if you're interested in the fine details. The basics of it is I know in Norway they vaccinate all their fish. There's roughly 300 million fish a year they produce. They vaccinate everyone. So for this technique, we simply just add our barium markers into the vaccine. So that way, if we get the concentration right, effectively what happens every time the vaccinated fish, it gets marked at the same time. We purchase I call them barium salts, basically because if you know normal table salt, which is sodium chloride, looks like a nice white crystal, and sodium chloride salt dissolves in water very easily. We purchase our barium salts in barium chloride form, which also just dissolves in water the same way. So it's very easy to use. We dissolve it in a little bit of distilled water, and then it's added that dissolved solution. We dissolve it to a certain concentration, then it's mixed with the vaccine. The vaccine that we've been using for our trials in Norway is Minerva 6, so it's a multi-vaccine. You need to make sure it's mixed thoroughly. And then standard vaccine gun is the best way to use it, and simply vaccinate your fish. Injection doses, we calculate everything on an injection dose of 0.1 of a mil, which again is standard in Norway. So that's how vaccination works. How does a mark? What does a mark look like? Again, in our trials, we've gone through and tried different concentrations to try and get down to the minimum concentration required to get a nice clear mark. See the dark blue line there, but also well above our threshold limit. Again, you can see the light blue line is a control fish. Again, nice and stable. Our mark fish is very obvious there. I'll just point out one more thing there. On this right-hand side of that graph, that is roughly in the core of the otolith. Notice for this vaccination technique, there's no mark in the core. The mark is out closer to the edge, because basically this fish was analysed only about 8 weeks after it was vaccinated. So just keep that point in mind. I'll come back to that later about where that mark is. For this technique, we've actually validated 4 successful different forms of barium, so 137, 36, 35 and 34, and we already know the minimum concentration we need to use is 0.0001 micrograms of barium per gram of fish. So I like to call that, it's a very small bit of pixie dust. It's next to nothing. When we use, I'll put that in context later on when we start talking about marking 300 million fish. When we start using combinations of marks, because there's a little bit of competition between isotopes, we actually have to increase the concentration to 0.01 micrograms of each of those bariums per gram of fish weight. When I say per gram of fish weight, it's just calculated on the average weight of basically the population that's going to be vaccinated. So if they've got 10,000 fish, and they'll go take a subsample, maybe measure 50 or 100 of them, not even say 50 of them, get an average weight, and we only have to estimate our concentration on the average weight of the fish. So there is a bit of room. You know, some fish can be 75, 100, and some can be 25, and we still know, based on these concentrations, that all those fish will get marked. So we're not doing a new concentration for every fish. It's just based on the average. Okay, on to our second technique. Now this technique's egg immersion. We call it egg immersion. This is actually the first time anywhere in the world this technique has actually been successfully run. In the past they've tried to mark eggs via egg immersion, but they've done it at later stages, not just at spawning or fertilisation, and they've been unsuccessful. But for this technique here, I noticed another observation in Norway, looking at YouTube on seeing how they spawn their fish in what happens after they've stripped the eggs and the sperm and then before it goes into the hatchery rearing trays. And notice a lot of places they strip the eggs and sperm out, fertilise the eggs, then they go tip a bucket of water on top of the eggs or fill that bucket up and they actually let it sit there for a couple of hours while the eggs swell and then they go and put the eggs in the hatchery. And I thought, well, that's a good place where they tip in that bucket of water and we could add our barium solution at the same time. And again, this paper's published if you want to read it. And so basically that's what we did. So basically here, this is done in the Matcha Research Station in Norway. Basically we're stripping eggs and sperm. We fertilise the eggs for a minute. And then after 1 minute we pour in our barium solution. This time the concentrations, when I say barium solution, we've got to have a couple of litres. So basically for 1 litre eggs we use 2 litres of solution. And the concentrations here are calculated on how many micrograms per litre of immersion solution we need. We just let them sit there for 2 hours, and over those 2 hours we actually sort of measured how much they increased. And those eggs swell by at least 10%. And so basically as they're swelling, I shouldn't use the word suck up, they suck up water and they suck up the barium. And then after those 2 hours those eggs actually start to go a bit hard and that barium actually stays retained in the egg. We don't know specifics of how it's retained in the egg, but we just know it is. That's another whole PhD in itself. But after those 2 hours, we simply drain off the barium solution, and then those eggs are just transferred into the hatchery rearing trays. And that's it. There's nothing else left to do for that. On to analysing an otolith that's been marked by the barium solution. Now this is different. The mark is in a different spot compared to vaccination. So again, 0 is the surface of the otolith. We're drilling towards the core. We're using the same spot size. You can see 157 microns looks huge on this otolith, basically because this otolith has just been taken out of a larvae just before it goes to first feeding. But you can see on the edge of this otolith there's actually no trace of our barium-137 mark. But as you go in, you can see the embryonic stage where the otoliths start to develop, which is basically at 200. In that area there, there's quite a distinct difference in the ratio. So we've marked this otolith right in the core. And that's basically because we've had that barium solution exposed to that fish right at the beginning of otolith development. So that's our second. So for the second marking technique, for this technique, we've got 3 different bariums to work. So 137, 136, 135. And again, if you've got combinations of 3.5 and 3.7, you only require 100 micrograms per litre. Again, these are the minimum amounts that you need to get 100% mark success. When I say 100% mark success, I mean every single fish in that batch is marked. When we use the triple combination of all 3 bariums, we actually need to increase that concentration to 1,000 micrograms per litre. Moving on to the third technique, transgenerational marking. This one's actually been around for quite a while. It's been around since 2006. There's a research scientist called Simon Thorold. He actually lived over the hill, I found out, from where I lived in New Zealand about 25 years ago. I think it's ironic that I'm following on from his work. But for this technique, it's called transgenerational marking, or I call it marking via maternal transfer. So in other words, you apply your barium solution or your barium spike to the brood fish, and then it's transferred from the brood fish to the eggs in situ, and then those eggs are spawned, and you have the mark in the core again. This is also published. If you want to read about this technique, the basics of how it works. Again, this is done on the Matcha Research Station in Norway. We sorted the fish mature fish a couple of months before spawning, and they come from the sea cage and go into freshwater tanks. We inject the female brood fish with our barium solution, optimally 3 weeks prior to spawning. You can't always guarantee that, so this was potentially one of the weak points of this technique. But again, that is all you're doing. Then it's basically once they're ready to spawn, you spawn, fertilise the eggs, and put them straight into the hatchery. So again, here you've got one injection that potentially marks 5,000 to 10,000 fish in one go. So how do these marks look? I've put two lines on this graph because I want to show you just the difference between concentrations. Again, that otolith is it's the same otolith as before, but it's just for presentation. Again, it's a larval otolith just before it goes to first feeding. We've got a large spot size, and again we're drilling drilling from the edge of the otolith towards the core. You can see in the graph here that pretty much the majority of the entire otolith is marked. It's starting as 200 is the core. You can see that's the highest change in ratio. It's been the greatest uptake of our marker, again because it's the early embryonic stage. But as it's starting to grow, you can see it's already starting to come back to the natural ratio. The reason I have two lines on this graph, so A is a concentration using 0.2 of a micrograms per litre, and B is using concentration of 0.02, so 10 times less. So, but here we have an interaction as well. It's not shown, but this is all good when you have 3 weeks between the day you injection and the day the fish spawns. If you inject the fish 24 hours before and it spawns, it'll end up like the blue line. You won't get your mark. If it spawns a week before, only a week after you inject, your higher concentration won't be a mark like A. It'll look like a mark like something like B. So you don't get as much uptake. But again, you get marks in the core, so it's still a good technique. And it's successful. For this technique, we've validated all 4 different forms of barium. So 137 right through to 134. Again, we have the concentration varies on what combinations we're using. So 137, 135, you only need 0.02 micrograms. This time it's per gram of brood fish. So basically we measure the average weight of all brood fish. So you'll get an estimate, say the average brood fish weighs 10 kilos. You'll calculate the dose on 10 kilos for all the brood fish in the tank. Generally speaking, you'll get some fish that are 14, 15 kilos, some are 8 kilos, but the concentration is strong enough and robust enough to make sure it doesn't matter about that variation in brood fish size. And again, you'll get some fish that only produce a couple of thousand eggs, and you'll get fish that produce 10,000 eggs. The only other thing I'll say about this one, the most important thing about this technique is you actually need to make sure there's time between injection this morning, at least 3 weeks. All right, so how do these techniques compare? I've given you 3 different options. This is hypothetical here, but this was actually, I've made this slide, this was for the Norwegian industry, because at this stage they're all about, we're going to mark all our fish somehow and solve, we're going to mark all the fish. All the farmers are going to know their fish are marked, and therefore they're not going to let them get out. We know that's not the case, but I still put up this hypothetical idea. What if we did actually go mark all 300 million fish in Norway? So you've got your vaccination technique, your egg immersion technique, and your maternal transfer. I've tried to make this relative and purely in the amount of barium that we use to mark that many fish, rather than use dollars, just to keep it hypothetical. So for the vaccination technique, I know we use about 15 grams. You'd use about 15 grams to mark all 300 million fish. To put that in context, if you're using the egg immersion technique, even though we've calculated how much barium we need per litre rather than per fish, you'd still need about 15 grams. So those 2 techniques at the end of the day would use the same amount of raw material to mark that many fish. Again, with our maternal transfer, if you roughly do the numbers, and this is very rough, this is saying 5,000 eggs per 10 kilogram brood fish, 60,000 brood fish. You'd actually use a little bit less, so you'd use 12 grams. That might not, it might seem quite a, 15 grams here, 12 grams here. It seems there's very little difference, and that's my point. There is very little difference between these techniques and the amount of raw material. The more important thing to take away comparing these techniques is the time when you actually mark. If you think about it, this bottom one, maternal transfer, first of all, you've got to inject brood fish. You might only have 9 out of your 10 brood fish actually spawn, so you lose 10%. Then you might only have 80%, you might lose another 20% of those eggs that don't hatch. So then you lost a total of 30%. So you actually mark 30% of fish you're not even going to use. When you go up to egg immersion, well, you know you've got all your eggs, so you don't have to worry about the spawning part. But again, you might lose 20% of your fish because those eggs don't hatch. So again, you're marking a lot of fish that don't get used. When you go to your vaccination technique, by that time, you pretty much know it should be, or in Norway, it should be, 95 to 99% of those fish are going to survive. So at least by the later you mark in the stage, if you're going to put your effort to marking fish then, you're marking fish that are going to be there and actually grow in cages. So just keep that in mind. Another way to compare techniques is actually, this is purely effectively this is for me, or whoever's going to analyse these fish, is actually detecting these marks and how easy it is to detect them. This is a experimental fish. So this fish was actually marked during the egg immersion experiment. And right at the end of my PhD, because I had a little bit of barium left over and I had nothing to do for a day, we thought, well, how about we go and mark it via the vaccination method as well, just to see, can we get a double mark, and you actually can double the amount of fingerprint combinations quite easy if you do it this way. But more interesting, I'll put this graph up just to show you the difference in detecting marks. So the egg immersion mark is on the right-hand side here, and that's in the core of the otolith. You can see above our threshold limit, it's not very high, but it's quite wide. To detect that mark in adult fish, we have to make sure with the laser we actually hit the core. And the core of that fish is only about 300 microns wide. So it's not like trying to find a needle in a haystack, but it's like me sort of trying to hit the speaker over there. So it can be done most of the time, but there is a chance you might miss it. The vaccination mark is when the fish is a par. The otolith is a lot bigger, and that is a lot easier for us with a laser to hit. So that's like basically me trying to hit the screen. I can pretty much guarantee even a big fish, if that mark is going to be in the fish, we're going to be able to detect it. So just keep that in mind. It's another reason between deciding on which technique you'd end up using, purely for the ease of detection. Right, so can we use this to trace escapes? Like I said, all three techniques could be used. There are a little bit of difference between techniques. That vaccination method and the transgenerational method, we've got 15 unique codes. And with our egg immersion technique, we've got 7 unique codes. These are the ones that are confirmed. Effectively, we could use any one of those to give each company in Iceland its own unique mark at this stage. Like I said, Iceland's in the embryonic stage of salmon farming, I would say. So at this stage, this is quite doable. It can be done. Just on to a few other, there's always these questions about fish health. So putting barium into a fish, does it affect the fish? Is it dangerous for us? During our vaccination trial, we actually measured general fish health parameters. So basically, from the day that fish was marked, those fish have grown right through to production size. And we monitor their growth rate, their condition index, and their mortality rate. And this was compared to fish that were vaccinated, but not with the barium mark. And you can read the fine details about this in the Warren Myers 2015A. But effectively, we found no effect of the barium mark on fish. And I'll explain a bit more why we've pretty much found no effect in a minute. The other question that everyone asks is, well, hang on, you've put barium into the fish during vaccination. When I go to eat that fish, is there still an increase of that barium mark that I've put in there? So we've actually had the flesh analysed of those harvest fish from that trial, and they went and look at. This was done independently of me. It was done by another laboratory at Melbourne Uni. They went and measured the ratios of our rare elements, or rare barium forms of barium that we put in, and they measured those ratios again. So 137 to 138, 36 to 38, and so forth. and we found that those levels completely back to normal background. So there's no trace in that fish, in the flesh. It's still there in the otolith, because it's preserved in the otolith, but there's no trace in the flesh of our marks. Just to give you an idea, the other question was, well, you know, I've measured it in a 5 kg fish. Was it still there at 4.99 kgs and I just happened to pick the right time? I cannot say yes or no, but I can give you an indication of just how long that mark stays in the actual fish. So going back to that graph again, if we look with our fish here that was marked with egg immersion, I'll stand over here. Basically, by the time you get to about here, we know that that fish is now feeding. It's gone into the next stage of hatchery, so it's on pellet feed. And you can see the ratio there is actually, it's gone well back down the background. So basically, there's no remaining marker that we have that's been uptaken to the otolith, which would indicate there's actually no barium mark left in that fish. And you can see it's nice and stable again until we go and vaccinate it again, where we manage to increase the amount of barium again. But very quickly again, you see it drops off and starts dropping back to background again. And there's only 8 weeks between here and there. So it gives you a good indication, it's another 18 months for that fish from vaccination to get up to harvest size. But the reality was that I'd say, going by the graph, you'd say 2 months, but you could conservatively say within 6 months you definitely can't find any trace of that marker anymore. So that's good to know. If you're eating a full-size fish, you're not eating any of my barium marks, so your air bones won't be marked. Moving on to Iceland. So what about here? What if we want to use the vaccination method here? I understand your current production, I've been told, there's 5 or 6 companies, you're producing about 10,000 tonnes, which is about 2 million fish. Compared to Norway, that's nothing. That's 150th of what they do in Norway. Your future production, I hear, I don't know how many companies they're going to be, but it's supposedly going to be somewhere around about 70,000 tonnes and 114 million. Again, it's very small compared to what's happening in Norway. Still based on 6 companies, Leo and here, we've had this collaboration on doing a pilot to actually see if we can develop the 6 codes for marking Iceland fish, so that each company in Iceland has its own mark. We're just fine-tuning the minimum concentrations we need to use, but we've already, these are the 6 codes. So close your eyes, you're not supposed to look at the codes. These will be the 6 codes that we've developed here. And we've already validated that we know these 6 codes will work. We're just fine-tuning the concentration at the moment. But just to give you an idea, this is a double marks. This is fishes marked to 135 and 137. The flat line is our 3 standard deviations above background. As you can see at the moment, we've got massive marks. We don't need to use this much isotope or barium to mark the fish. But that's a 135, 137 mark. We've also developed our 136, 137, again, nice and clear. And again, you can see their vaccination marks. So they go up very quickly and they come back down to background very quickly. And that's our 3rd mark. It's a 135, 136 mark. We also have our 3 single marks which we developed. So there's a 135 mark, a 136 mark, and a 137 mark. Like I said, we've verified, we know we can use these 6 fingerprint codes now. We will hopefully try and reduce the concentration a bit more so we can get nice, consistent and low marks. But again, they will be, when we analyse them, when I sit in the laser room and I see the raw printout, I want to see this coming across the screen, so it makes it very easy. Just to give you an indication of time, the time it takes to run that through the laser is about 1.5 minutes. So it's very quick we can probably do 100 to 120 otoliths in a day once we're set up and running, and once we have the system set. If anyone wants to go away and read the fine details of any of these techniques, like I said, they're all published. If you Google my name, you'll find these publications on Google Scholar. Please have a read. If you have any questions, please feel free to come and ask me. And This is the picture I took of your lovely Iceland today while walking to the Institute, and thank you very much.